Hello, hi everyone, and welcome to another measurement and instrumentation class. So previous class, we went actually to the lab and did some experiment. I've already sent a lab manual to online students. And before that, we had our second exam. Today, we're gonna finish the sensor technologies. We already went through sensors before. I wanna dive deeper into that, into the sensor technology and different technologies that we have. And next week, if we have time, we'll go through biosensors and a review class for the final exam if we have time. Your final exam, I think it's the same time as the class. I'm not sure. Please double check it, but I will send another announcement for your final exam. The final exam is going to be a complimentary, so everything would be included for the final exam. The number of questions would be more compared to the previous exams, but the format, everything is going to be the same. Now, quick review of what we learned about sensors and sensor technology. First thing that we learned about sensors and the characteristics of sensors is their ability to measure something in a linear form. What does it mean? It means that if you're measuring amplitude, phase, it must be linear. So if the true value, if it's increased 2 times, the measured value should also be increased 2 times. If it's nonlinear, we're going to have problems. So one of the main characteristics of sensors must be linearity, and we already spoke about that, and it should be about phase, amplitude, frequency, everything. We also spoke about some terminologies of sensors, what a transducer is. Transducer is a device that converts one form of energy to another form of energy, or one form like voltage to current, current to voltage is also considered a transducer. We do that using op amps. Also, if you're converting mechanical like voice, air pressure, temperature to electrical, that's also called a type of transducer as well. And typical energy domains are mechanical, electrical, chemical, magnetic, optical, and thermal. So we have, temperature sensor, humidity sensor, pH sensor, which is chemical, and a ultrasound sensor, which is a mechanical. Now, transducers can also be further divided into sensors, which monitors a system, and actuators, which impose an action on the system, like switches and so on, and motors and step motors and so on. Sensors are devices which monitor a parameter of a system, hopefully without disturbing the parameters. Some categorization of sensors, we already went through that. We have mechanical, like strain gauge, thermal, like thermocoupling, optical, magnetic, and so on. We had classifications based on measuring mechanism. We had resistance, capacitance, inductance, piezoelectricity, and so on. Magnetic as well is another one. Photodiodes, it's another one that works with light. And then we have materials capable of converting one form of energy to another, such as what we call smart materials. And these smart materials, they act like a piezoelectric system. Now, some consideration in instrumentation, we have sensor technology. We already went through these. Sensor data collection topologies, like A to D, D to A, data communication systems, power supply data synchronization, environmental parameters and influence, and remote data analysis. This shows a graph of a measurement system. We have the physical phenomena. We have the sensor system and the measurement output, which measurement output could be a compressed data that is sent to a Arduino, Raspberry Pi, or microcontroller or microprocessor. And we already know the definitions of sensors, which are devices for sensing physical variables of a physical system or an environment. And we went through the different classifications: mechanical, thermal, chemical, electromagnetic, optical. Some specification of sensors, we had accuracy, resolution, sensitivity, and repeatability or precision. We spoke about accuracy and precision, if you remember the targets that we had. This is another example of accuracy versus resolution. You can see that this system, the resolution means that it could measure very, very fine values. An example is, imagine you have two multimeters. One could measure in half a volt increments. One could measure in 0.01 or 1 millivolts or 10 millivolt increments. So the one that could measure 1, 2, 3 millivolts has much higher resolution compared to the one that could only measure half a volt. Okay, and accuracy is the closest that we get to the actual value. And here this graph shows a very interesting picture of the difference between the resolution, which is the steps and the difference between steps that we can get, and the accuracy, which is the difference between the true value and the measurement value. Now, we already went through this. This is a comparison between accuracy and precision. The one on the left, we have a precise system without accuracy, so precision is high. Without accuracy, second one, accuracy is higher because it's around the target, but it's scattered. And the third one on the right, you have very high accuracy, high precision, which is a desirable one. This one you can easily fix by shifting. So if you have a bias, you can easily subtract that and shift this. This one you can also easily fix by averaging, meaning you take the average, what we call different type of systems like KNN, nearest neighborhood. We find the center, and we average all the values, you get the sensor, and then you subtract everything from that. But if it's not accurate and not precise, it's going to be very difficult to fix that issue. Some specifications of sensors, we have dynamic range, linearity, transfer function, bandwidth, and noise. We already went through all of these. This is just for a reminder. Some attributes of sensors, we have operating principles. These are embedded technologies that make sensors function, such as electro-optics, electromagnetics, piezoelectrics, and active and passive ultraviolet. We have dimensional variables, the number of dimensions of physical variables. We have the size, which is the physical volume of sensors. We have data format. Is it in time domains, frequency domain? Is it digital? Is it analog? So on. We have the intelligence, the capabilities of onboard data processing and decision making. We have active and passive sensors. Active ones, they have a power source. It must be powered to work. Passives don't require that. It actually works on purely on its internal energy. And then we have physical contact, the way sensors observe the disturbance in environment, and environmental durability. Will the sensor be robust enough for its operation condition? Now, the part that we haven't gone through deep enough is going to be the different type of sensors, how they work, and also MEMS. If I have time, we can go through MEMS. And I'll explain what MEMS are. Now, the most famous one and the easiest one is called the strain gauge. We have different type of strain gauges. We only briefly studied one of them, which is called the foil strain gauge. The foil strain gauge, and I already showed you the picture, looks like this. You have a bunch of wires going in zigzag and twisting around. This is the cheapest strain gauge. It's widely used. but it has some drawbacks. First of all, it's not meant for long distances, meaning if you want to, find the strain on 10, 15 centimeters, if you stretch it that much, it's going to rip off the sensor. So it's built for very small changes in distance. If you want to measure long distances, it's not going to work at all. Another thing that is a big drawback as a system is, what does this sensor look like? If you didn't know this is a strain gauge, what comes in mind immediately when you see this? If I didn't tell you this is a strain gauge. Heating element, yeah, that's a good one. Why do we make a heating element like this? Yes, because we want to have a maximum radiation. Yes, maximum surface. And that's the principle of when we build an antenna as well. So if you open a smartphone, you would see that the antenna is actually going around it because you want to have maximum surface. And of course, it depends on other things like lambda, which is the delta lambda, the frequency, all of that. But this looks very similar to an antenna. I don't know if you remember, if you had those old radios or TVs, analog TVs that had these antennas. This looks like an antenna. So what happens if you make a coil or a mesh like this? It acts like an antenna. So all the magnetic field that you have around you is going to have some effect on this. So this technically acts like a magnetic receiver as well, like an antenna, and it produces a little bit of current. And the current difference that we have when we have a strain gauge is very small, by the way. Imagine you have this acting like the magnetic receiver or antenna as well. So that current is also induced, and you're going to have error. So another big problem of these systems is going to be its electromagnetic interface. And another thing, it's the other drawback that it has, its sensitivity to heat and moisture. The reason it's very sensitive to heat is because usually this is a very fine copper wire inside a resin or plastic. So it's pressed between two layers of resin or plastic to protect that inner, copper lining. When it becomes very cold, it becomes very fragile. It could easily break. When it becomes very hot, it becomes, elastic. It's like a rubber band. And the other thing is, the heat also affects the internal resistance of the copper wire inside the strain gauge. So you're going to have a double effect. And also humidity as well. It has effect on the conductivity and electronic properties of the system. Therefore, this is another drawback of these. There are some ways to mitigate these problems. For example, when you want to reduce the electromagnetic field interference on these, you just use a cage, a Faraday cage, what we call, around it. Or you put it in another shell if you want to reduce the heat, or you can use heat sink or fans or so on. But most of the time it doesn't make sense because you're adding more to the system. This is for a very cheap system. You don't want to make it expensive and bulky. Now, another type of strain gauge is called the vibration wire strain gauge. It determines strain from frequency of an AC signal, and this is very bulky. It's like this again. Again, you have a vibration. It changes the distance between two conductors, changes the frequency, and you can determine the strain on the system. And another one is called a fiber optic gauge. And this one actually looks like this. You have a pulsating light or signal going through that. And when you stretch it, you're increasing the distance, you're decreasing the diameter, and you're creating a little bit of wavelet difference. And you can see the input light, the reflected light, and the transmitted light. And from this small distance, you can measure, or small gap, you can measure the amount of stress that you have or strain you have on the wire. Now, the good thing about fiber optics, it's immune to electromagnetic fields and electrostatic noise. So anything electrical, magnetic, it's not going to affect it. It's compact, but it's high size, high cost, and it's very fragile because technically in the middle it's glass, and if you bend it, it's going to break, or if you too much pressure on it, it's going to break. This is the reason that we use this type of sensor in MRI devices. Anything that is connected to a patient in an MRI device, it's made out of fiber optics. So if you want to put what we call an EEG, which measures brain signal activity, all of those, in a normal condition, they are made out of copper. But in an MRI device, everything is made out of fiber optics. The reason is because if you put any type of metal inside that electromagnetic field is going to interfere with that, and you're not going to get the results that you're looking for. So yes, you're comparing frequency senses, and it's like this. Imagine you have a wire and there's electric signal passing through it. If you stretch it a little bit for a microsecond, you're increasing the period. And that little frequency distance, and that frequency is so high that you can pick up that, okay? But again, very high frequency system, and you need a very accurate signal processing tool at the end to be able to process that. And you need to synchronize the input and the output to match the frequencies. So you're going to have a little bit of shift and a little bit of frequency distance, and by that you can determine the AC signal. That's the reason we don't use that much. I have barely seen them. And even the strain gauge that you can see here, it's mostly repaired with other techniques. Let me give you an example. We don't use strain gauges now on bridges anymore because it's going to be difficult. You have to put it on a bridge. It's going to break. It's not going to last very long. What we do, we use image processing. So what you can do is you can put like two dots on the bridge, and the bridge, when it starts moving, a camera can capture that. This is one example. Mm-hmm.
Receiver up on top,
Mm-hmm.
pole, right?
Yes.
We have different antenna things.
Yes.
You select between long and short. Is that similar to that concept?
Yeah, for the second one, you can say a little bit similar, but the size of that lambda is equal, or I don't know if you're familiar with Shannon theory, it's half of the frequency. So the exact size of the antenna is relative to your lambda, which is your frequency length. And that's the potential. So if you have an FM frequency, you have a different type of antenna. So this lambda should be actually equal to your, so if this is your antenna, this and this should match. This is the reason we use modulation. If you don't use modulation and you just want to send voice signal, the length of your antenna would be around 1 mile, roughly 1 mile. That's the reason we go very high frequency. We use modulation. Modulation, you have a carrier frequency. So this is a different topic. It's from signal systems and communication systems, but I'm just going to briefly mention it. So what we do in a signal, if you have, for example, AM, do you know what AM stands for? Amplitude modulation. Okay, so amplitude modulation, you have this frequency, which is your voice frequency, okay? But this frequency is very low. It's like 30, 40 hertz, something like that. If you want to send this, it's not going to go far. You need very large antennas. I'm not going to go through the equation, but the equation, you're just going to have like something that is 1 mile or so. So the thing that you do, you use a carrier signal, and this is our carrier signal. It's a very high frequency signal that carries the lower frequency signal. So you end up with what we call a envelope signal, okay? So this is what it's transmitted, the one in the middle, but what it's carrying is its envelope, its shape, okay? This inside, this frequency is for like a FM, it's 104 megahertz. Let's say it's 90 megahertz. Okay, so this inside it's 90 megahertz and it's fixed. We don't change it. The only thing that we change its amplitude. We're alternating its amplitude. And the signal that we have on top, which is its envelope, this is the carrier signal and this is the information signal. This is around 30 hertz. And what we do in the receiver, we just use what we call a envelope detector, which is technically a diode, resistor, and a capacitor. And we'll connect these dots. It's like a analog to digital, and we extract that. So in the output, we extract this, and then we push it through a amplifier, and we can hear it. So by slightly changing the frequency, we can go to different stations. So from 90, if you go to 100, you can pick up 100 megahertz frequency or 150 or so on. So AM looks like this. FM frequency modulation is completely different. You have a solid amplitude, but the frequency is changing, okay? So this is, for example, 0, 0, this is 1, 0, this is 1, 1. So by changing the frequency, you convey the information. And then we have QM, QPM, QAM, different type, which those are phase shifting. I don't want to, it's a complete different course. You have communication systems 1 and 2, which are analog and digital. But for now, know that this signal frequency determines the size of your antenna. This is the reason, if I'm old enough to remember these old smartphones, they had these expandable, drawn out antennas, and you had to draw them out to start speaking. The reason was the first and second generation 1G and 2G cell phones, they worked on a very lower frequency and differences compared to now. Now we have higher frequency around 2.4 gigahertz, 5 gigahertz. That frequency has extended. You need just smaller antennas. And on top of that, because you have a higher frequency, you need what we call more of these cell phone towers. So you're much closer to them. You require much less power. That's the reason you don't need a big, bulky phone that it's like, a size of a brick. And like 70% of that was the battery because it required a lot of power to send the signal for long distances. Anyway, so high frequency is good, but it has its own problems. You can't pass through objects. So 6G, it doesn't work even in rain. 4G, it could pass walls, thin walls. 6G cannot do that. That's the reason if you have 5G or 6G, which is coming, 5G even, you need to have what we call BTS, cell phone towers all around. Not the BTS, Korean group. BTS, the cell phone, for the cell phone. Anyway, let's move on to the foil strain gauge. So foil strain gauge, we have different types of that as well. The advantages of foil strain gauge is that the technology is well developed, it's low cost, it has a high response speed and broad frequency bandwidth. It has a wide assortment of foil strain gauges commercially available, subject to electromagnetic noise, interference, offset drift in a signal, and the long-term performance of the adhesive used for bonding strain gauge is questionable, as mentioned. When it gets hot and cold, it tends to, rip apart. And the vibrating wire strain gauge cannot be used for dynamic application because of their low response speed. That's the reason we use optic fiber strain gauge for that. Another type of strain gauges that we have are called the piezoelectric strain gauge. Piezoelectric is a polymer-based material. We call them also PVDF. And the way that they work, and I've already explained this before, but it's a type of material in which when you squeeze it or when you expand it, it creates a little bit of voltage. So if you squeeze it, you're going to have a little bit of current passing through it. Okay. Imagine you have a balloon full of water, you squeeze it, a little bit of water comes out. And it's very good if you want to create pressure sensors with them or strain gauges. The only problem is they can't differentiate between X, Y, and Z axis because you don't know which way you're putting pressure to it. You just squeeze it, it produces a little bit of current, but it couldn't determine which way did you squeeze it. Did you squeeze it in the X direction or Y direction? Which one did you squeeze it? It looks like that. Another type of sensor we have is called the piezoelectric accelerometer. These are non-zero lower cutoff frequencies, about 0.1 to 1 hertz for 5%. They are light, compact size, miniature accelerometer weighing about 0.7 grams is also available. The measurement range is up to positive negative 500 G, which is great. And it's less expensive than capacitive accelerometers. The sensitivity is typically from 5 to 100 millivolts per G. And the broad frequency bandwidth is typically from 0.2 to 5 kilohertz. And the operating temperature is negative 70 to 150 degrees Celsius. So it's pretty good. And the way that a piezoelectric accelerometer works, or acceleration sensor, we have the piezoelectric in the middle, pressed between two conductive coating, and these conductive coating is to pass the current or electric current or charge that it produces. Then we have a mass connected to that. We have a damper and a spring. And the sensor itself is connected to a vibrating surface. And we have a mounting stud. And imagine that the vibrating surface is moving upwards. What happens is this mass pushes inwards, and now it becomes here. And when you squeeze the piezoelectric, it's going to generate a current, and you can measure G-force. Now, if you put another one, if you rotate it 90 degrees and put another one here, the same piezoelectric, you can create an accelerometer that works in two directions. And if you put another one 90 degrees going towards you, you can make it three-dimensional accelerometer. Now, where do we use accelerometers? Perfect. Gyroscopes, drones, phones, everything that you see around you, they use electronics. Now they have accelerometers. Airbags for cars. Those are different type of, but you can still use them. So if you have an accelerometer sensor on your phone, and I happen to have one here, and you can see the X, Y, and Z axis. And if I start moving it in different directions, you can see the acceleration going. You can see it. And I have a bunch of these sensors, very important. Now, these also are used in your smartwatch. Why do we use them in smartwatches? Yes, to track your steps, okay? So tracking activity is one thing that they do, because when you walk, you move your hand, it could measure your activity. Gyro and accelerometers are a little different, but almost in the same category. The other thing, they are used for fall detection. So if you have a crash, a fall, Apple Watch can detect it using its accelerometer. They have a threshold G. If the G is above a certain, it detects an accident. Now, yes. Yes, unless you have multiple and it's a accelerating sensing system. Okay, because this one has its mass, it's sandwiched between two masses, so you would know exactly which way the pressure is coming. Still, we don't use them that much. Another type of acceleration sensor we are using is called the capacitive accelerometer. This has very good performance over low frequency range and can measure gravity. So gyro is actually a type of accelerometer. And the way that these gyro systems work is, and can you give me an example why we use gyroscopes and gyros? Where do we use them? Planes. And another thing is actually in your phone as well. Your phone, you have a rotation pin, and if you move it horizontally, what happens? This is a gyro. It measures the gravity, so know which way is down. So gaming on your phone have a gyro, and it detects the gravity and detects where it's down, which way is up. You have it on your phone, your watch, especially on the drones as well. It could determine which way is down. Yeah, they use it a lot in aerospace as well. A lot in airplanes. They have mechanical ones, which is basically a weight or a magnet. But these newer ones, electrical ones, they use capacitor type as well. They are heavier, around 100 grams, and bigger size than piezoelectric accelerometers. Their measurement range is up to plus negative 200 Gs. 200 Gs is enormous G-force. It could rip someone apart, okay? I think the astronauts, when they feel like 10 G, 12 G, something like that, this is like a huge force. It's more than a crash. These are more expensive. Sensitivity is typically from 10 to 1,000 millivolts per G. The frequency bandwidth typically is between 0 and 800 hertz. And the operating temperature is pretty good, negative 65 to 120 degrees Celsius. Now, the way that a capacitive accelerometer or accelerating sensor works is like this. You have a seismic mass in the middle, and then you have fixed plates. You can see the fixed plates, and all of this is in an enclosure, okay, in the sensor. Now, what happens if you move right or left? This mass is going to move to right or left. And when you move right to left, the distance between these two capacitive plates changes. Okay? Do you remember the relation between distance between the conductors and the capacitance? So the larger the distances, you're going to have a smaller capacitance. So it had an inverse relation with the distance. Obviously, you can't change the area, but you can change the distance. So the higher the distance you're going to have lower capacitance, and the lower you're going to have higher capacitance. So therefore, you're changing capacitors A and B. And by changing capacitance A and B, you can measure how much G-force you had and how much movement you had. You use this a lot again, and these are older generation, I would say, in phones that we had. Nowadays, we use MEMS, and I'll explain what MEMS is. It's exact same principle, but in a very, very small package. You directly build it in an IC using semiconductors. You don't need these, mass and springs. You don't need any of these. Instead of the springs and these plates, everything is built out of a single material, which are semiconductors. Now, another type of force sensing is called the metal foil strain gauge based or load cell. These are good and low frequency response, high load rating, resolution lower than piezoelectric base. They are rugged, typical big size and heavy weight. These are the ones that you may see typically in a construction, a bridge or something like that. It uses the same principle, but these are made out of metal. They are very rugged. They can measure very low strains, but they are good for robust systems. Another type is called the piezoelectricity based force sensor. They have lower cutoff frequency at 0.01 hertz, cannot be used for static load measurement. So if you want to measure a bridge's weight, it's not going to work. But if you want to use it as a scale, and most of these digital scales that you may have in your what they call bathroom scales that you have in your home, these use a piezoelectric, so they have you have four different points that is connected to the ground, four pillars, and you put one on each, and you can measure weight. These are good in high frequency, high resolution, limited operating temperature, and cannot be used for high temperature applications, and they have compact size and very light. Another type of sensor that we have is called the displacement sensor or sensing system, or what we call the LVDT, or linear variable difference transformer. These are inductance-based electromechanical sensors. They have infinite resolution, limited by external electronics. They have limited bandwidth, 250 hertz typically for DC LVDT and 500 hertz for AC LVDT. They have no contact between the moving core and a coil structure, no friction, no wear, very long operation life, and accuracy is limited mostly by linearity, about 0.1% to 1% typical. The models with strokes from millimeters to 1 meter are available. Now, these sensors are used in linear actuators. So if you have a robot and you want to measure how much the arm is extending or something like that, these displacement sensors work very well. So for different robotic applications, these are actually used. And a different type of these displacement sensors are linear potentiometers. And the resolution, again, is infinite. It depends on the steps and the difference between the resistances and how big we can build this resistor. They have high frequency bandwidth above 10 kilohertz. They have fast response speed. The velocity is up to 2.5 meters per second. They are low cost, finite operating life, 2 million cycles, because it's going to wear down due to contact wear, as mentioned. Accuracy is about 0.0 to 3%. And the operating temperature is -55 to 125. So basically, when you move these and you retract or you spring and open this, expand it, the resistance between 0.2 and 3 and 1 and 2 changes. So, and by measuring the resistance, the further the distance, you're going to have a higher resistance. You can measure the displacement. Another type of displacement transducer is called the magnetostrictive linear displacement transducer. It has exceptional performance for long stroke position measurements up to 3 meters. The operation is based on accurately measuring the distance from a predetermined point to a magnetic field produced by a movable permanent magnet. The repeatability is up to 0.002% of the measurement range. The resolution is up to 0.002%, which is great, of the scale of full range. It has relatively low frequency bandwidth, very expensive, and operating temperature is 0 to 70 degrees because temperature affects magnetic field. So basically what this does, you have a magnetic or coil and a sensing coil, you send a pulse, and depending on how the magnetic field and the distance and the time it takes to move that magnetic field, you can detect the distance. Another type is called the differential variable reluctance transducers. They are relatively short stroke, high resolution, and they are non-contact between the measured object and the sensor. And the way that they work, again, you have a coil. It works on the magnetic field principles. The closer you get to that coil, the metal, you're going to have higher current induced. And the further you go, you have lower current that you would induce. So technically, it's like, imagine you have a nail and you put a wire coil around it, you're going to create a magnetic field. Now bring another nail close to it. The closer you get, you're going to feel more magnetic field. It's going to generate more current inside that second nail. Now, another type of sensor is called the velocity sensing. This is a type of scanning laser vibrometry. These are non-contact physical sensor technologies. They facilitate remote mass loading free of vibration measurements on targets. They measure velocity, and it could be translational or angular. They have automated scanning measurements with fast scanning speed. They are very expensive. This is an example which is used to measure the vibration on the engine of a car. These could also be used to detect, I've seen them to be, detect voice and, building vibration as well. One example is if someone is speaking behind this wall, you have a little vibration on the doors of the wall, you can pick it up with these laser vibrometry. Another application is for measuring heart rate and respiration, breathe. But the problem is it must be in contact with the skin, so privacy is a little bit, sketchy on this. No one wants to, just for measuring their heart rate, and you have to be still. If you move, it's not going to work. That's the reason we prefer, smartwatches. You have to sit still. It may have some application. I actually worked on this for a research project, and I have a paper on it. You can detect heart rate from a distance, what we call RPG. The only application that we could find was for neonatals, babies which are in ICU, because they don't move a lot, and they're so tiny that you can't put a sensor on them. So they prefer using remote, sensors for measuring their heart rate and respiratory. Still, it has a lot of, space to improve. It's not accurate, but it could be done. Yeah. So they wanted to put it on pilots as well to measure, pilot. But the thing is, the vibration is so high in an airplane and a helicopter. They use anything. So this is the benefit of these. These are called contactless, and it gained a lot of traction during COVID because you can measure temperature and heart rate, and you can determine if someone is infected from a distance. But after COVID went away, the buzz around it just faded. Then we have shock or high G sensing. These are used, for example, in airbags. These are shock pressure sensors. The measurement range up to 69 megapascal or 10 KSI. They are also sometimes used in air pressure and high pressure situations as well. They have high response speed, rise to less than 2 microseconds. They have high frequency bandwidth. The operating temperature is -70 to 130, and they are very light. And then we have the shock accelerometer, which are the measurement range are positive, -70,000 G, which is an enormous amount of G. Frequency bandwidth is typically from 0.5 to 30 kilohertz and at -3 dB, and the operating temperature is -40 to 80, and it's very light. It weighs around 5 grams. Now, we also have angular motion sensing or tilt meters, and these are some applications for them. We have the inertial gyroscope, which are used in Xbox, that you can see expo.com. They are using these in a lot of phones nowadays. They are using them in a lot of drones, and they're using for gaming as well. And then we have tilt sensors or inclinometers. This is from MicroStrain. This is tilt sensors and incremental inclinometers that generate an artificial horizon and measure angular with the respect to this horizon. We have also rotary position sensors, like the one that it's mentioned here. It includes potentiometers and a variety of magnetic and capacitive technologies. And sensors are designed for angular displacement less than 1 turn or for multi-turn displacement. Now, let's start with an interesting topic, which is called MEMS. I don't know if you've heard of it. MEMS technology, this is an acronym for microelectromechanical systems. And the name is given to the practice of making and combining miniaturized mechanical and electrical components. Sometimes we also call them micro machines and microsystem technologies in Europe and Japan. It leverages on existing IC-based fabrication techniques, but now extends to other non-IC techniques. It has a potential for low cost through batch fabrication, and thousands of MEMS devices scales from 0.2 micrometer to 1 millimeter could be made simultaneously on a single silicon wafer. It follows the same principle as ICs. The students who had electronics with me, I already went through these ICs and the fabrication, showed them some videos. But basically, a wafer, this is a wafer, this big disk, and a wafer is made out of silicon, 99.999% pure silicon. And we use different techniques like lithography to carve into that, and then we fill it with N junctions, so we create PN junctions and so on that. So we can create diodes and transistors and ICs, which are integrated circuits. We use the same principles, but we do the carving in a way that creates sensors. So co-location of sensing, computing, actuating, control, communication, and power on a small chip-sized device. The good thing about this, we can directly put the sensor on the processor. So it could be integrated inside an IC. Instead of having the sensor separate and you have to have a power source for that, communication algorithm, amplify it, you can directly put it inside the IC. You have high spatial functionality and fast response speed, very high precision in manufacture. Miniaturized components improve response speed and reduce power consumptions. And since you build them in a patch, they are very consistent. If you buy an individual sensor, you can't find two sensors that produce in the same factory that have same correct characteristics. But in a MEMS, you can make them more unified. And this is a fabrication process, very similar to ICs. We have a wafer, and then what we do, which is a thicker film with deeper etches, fewer steps that we have. And we have deposition of materials. We have pattern transfer, removal of the materials. Then we have probe testing, and then we cut it, make it sectioning, individual die, assembly into packages, package, seal, and final test. So the one that you see in the wafer actually inside that IC that you see, which sometimes is 1/100th of the size of the IC itself. But we have to put it in a package to be able to connect the pins, the terminals, and the power and signal and so on. And I'll show you how they work. So some distinctive features of MEMS devices. One is miniaturization. We have micro machines, sensors, and actuators can handle micro objects and move freely in small spaces. The problem that we have with normal sensors is because you have a sensor which is in an enclosed box. There is air between it. There is moisture between it. So if you take it from here to, let's say, Austin, you have different levels of moisture. And if you have a capacitor which has springs, after a while, those springs, what happens to the springs? They deteriorate. You're going to have, it's metal. What happens with metal when you have, and it's a very high humidity environment? It rusts, okay? So you're not going to have, and again, air pressure between those plates changes as well. Here we have high altitude, air is thinner, and Houston is thicker, so you're going to have different properties. When you make it small, like a MEMS device, those environmental factors have less effect, much less effect. And then we have multiplicity. The cooperative work from many small micro machines may be best way to perform a large task. It's inexpensive to make many machines in parallel. And then we have microelectronics, integrate electronic control devices with sensors and actuators. So we can put everything in a single IC. And this is a very interesting picture that shows that we have added, you remember a strain sensor, a strain gauge, you can print it inside an IC. Or you can print the accelerometer inside an IC. And you can see how small this is. This is around few micrometers. And you can see these, this is exactly the same as we had here. This is exact same sensor that we had here. These two sensors are exactly the same. This is a capacitive accelerometer. And this is a capacitive accelerometer. The only difference, I have printed this here. It's much smaller. It's made out of one single material, which is silicon usually. You don't need, springs and an external power supply. You can use the power supply. It's directly on the IC. You can directly send the signal to the processor to do, the processing on it. So capacitive MEMS accelerometer, they have high precision dual axis accelerometer with signal condition voltage outputs, all on a single monolithic IC. Monolithic means it's made out of single material. The sensitivity is from 20 to 1,000 millivolts per G, which is higher. We have very high accuracy, high temperature stability, low power. Power is less than 700 microamps, which is very small compared to an external sensor. And it's 5 millimeters by 5 millimeters by 2 millimeters, so extremely small, and an LCC package. And it's very low cost, about half to $1.4 per piece, 50 cents. For a normal sensor, that's going to be a couple of bucks. And the good thing is imagine you want to build a laptop, a gaming console, portable, or a smartwatch or a phone. Imagine like previously you used to put the sensor separately. Now it's printed inside the IC. So you can make it much smaller. The energy consumption is much smaller, less, so the battery is going to last more. So you have multiple effects. The phone is going to be lighter. It's going to last longer because that was a mechanical. This, if you fall, if you drop your phone, this is not going to happen. Nothing going to happen to this. That is going to have problem. If water gets in, this is not going to, have an effect on it. That one is going to, significantly degrade it. Another type is called the MEMS accelerometer. This one uses a piezoelectric MEMS, and you can see it's like a weight, which a mass that we have, and we have a lightly implanted piezo resistor. And what happens is when this moves to the left, one side compresses, the other side expands. So one side compresses, the other side expands, and you create a little bit of current, which you can detect. So it's basically like miniaturizing the accelerometer that we had in a very small footprint. And this is cut in half. The actual picture, this is the actual picture under a electronic microscope. I have a very interesting picture also that compares their size. Just give me a second. This stopped working. Now, as mentioned, a proof mass attached to a silicon housing through a short flexural element, the implementation of a piezo-resistive material on the upper surface of the flexural element. The strain experienced by a piezo-resistive material causes a position change of its internal atoms, resulting in the change of its electrical resistance and low noise property. It has low noise property at high frequencies. Now, this is a very interesting picture that we have. This is a comparison of the size of one of these, which is zoomed here, compared to a dandelion. And you can see how small it is. It's so small that literally it's like dust. Wind would take it away. It's going to float in air. It's that small, the size of this. And it's inside a IC. And this picture was like 5-6 years ago. And it's 10 times smaller than this now. So when you have it this small, instead of putting 1, you could put 10. Redundancy is another thing. So sometimes we need redundancy because if one of them fails, you want to use the other one. You have high G, you want to measure like acceleration in multiple directions. So instead of 1, you can put 3. And to increase your accuracy and your precision, you can use multiples of these in each corner of your device and use machine learning algorithms to detect and determine the optimal amount of acceleration. Now, these are now also used in cars, these accelerometer MEMS for activating the airbag. We have pressure sensors in the chassis, in front of the chassis, behind the bumpers. You have accelerometers. They're used, again, for airbags, for a lot of different applications you can use them. And for gaming and your joystick and your console, it's used a lot in your phones and so on. And they are embedded right now in what we call MEMS. And you can build different type of sensors using these accelerometers, pressure sensors, gyros, a bunch of different type of sensors. They're working on building new types as well. For example, one for, detecting blood glucose. Also, you can make that very small as well. So imagine you can build a glucose meter that is so small that you can inject it and it measures your glucose levels and it directly sends the signal to your phone or something. We also have these CGM, which are made pretty small right now, and they are working to make them even smaller. We have sensors that you can technically be implemented under the skin. They are used, I don't know if you follow, like Neuralink, they have some that you put in the brain and it could help people that are paralyzed to be able to move and speak again. Continuous glucose monitor. Yes, CGMs. We have 2 types. One that the drop ones that you pinch the finger, and the CGMs are continuous ones. I don't know if they've become very popular. You put it on your hand or butter bunny, and you leave it for a week or a month, depending on how much the butter lasts. It has a very small needle coming out of it. You don't even feel it. I used to use one for a week just to see how it works. And it has a memory on it, battery, and it sends the data on your phone. If you don't have any, blood sugar problems, I don't recommend using it because it's going to give you a lot of anxiety. It gives you alarms like now you have a glucose spike and now it's going down. So the anxiety itself is going to increase your blood sugar. But it's some people like it for not everyone uses for maintaining the blood glucose. Some of those are also connected to an insulin pump for those who have type 1 diabetes or some type 2 diabetes. The problem that previously occurred is, blood sugar dropped during the sleep and they went to anaphylactic shock. It's very dangerous. So this sensor monitors that, and if they need insulin, it's gonna, automatically the pump injects the right amount. You don't need to manually do it every day, and it's very accurate, saves a lot of lives. Okay, that's it for today. I've added some references. Again, next week I will continue and finish biosensors. And after that, we're going to review session for the final exam. Thank you so much, and I'll see you next week.